lecture in our triplet of enzyme lectures, our three-part epic. This is Enzymes 2, and we're going to be applying the Michaelis-Menten equation that we learned in the previous lecture and using that to examine different modes of regulation of enzymes in this lecture. We'll wrap up with the third lecture being about the different chemical reactions, all 6 different chemical reactions that enzymes perform. So far, we're familiar with the idea that enzymes are affected by environments. Weak bonds, pH, can change ionization states on amino acids and therefore can change the behavior of an enzyme, usually diminishing that behavior. We also learned that enzymes have particular characteristics. They are biological catalysts because the reactions of life occur too slowly to actually sustain life, and as catalysts they are not consumed by the reactions that they catalyze in general. We know they have specificity to their ligands. Ligand's just another term for a substrate. So they will recognize their ligand. They can be highly specific for a particular ligand down to chirality. They might be a little bit more generic, such as maybe they recognize proteolysis after basic amino acids or something like that. And they also have binding affinity. And the binding affinity we were able to measure as a function of the amount of substrate it takes to achieve 1/2 maximum velocity of the enzyme, which we denoted as Km. We also saw that enzymes often require cofactors such as NAD, metals, ATP, smaller molecules that are not necessarily part of the formal chemical reaction but are vital to the performance of the chemical reaction, and that enzymes allow the formation of the transition state of their substrate so they can proceed chemically to product, which is a very high energy state for the substrate, but the transition state is a very low energy state for the enzyme. We also learned that energetics is at the heart of biochemistry, and we looked briefly at free energy and determined that we can take the free energy of component parts of a system and add those together to get the free energy of the system. We also determined that if free energy is negative, a system would be favorable or spontaneous. If free energy is positive, the system would be not favorable or non-spontaneous. And if the free energy is 0, the system is at equilibrium. And we will also remember that free energy, or energetics, does not inform kinetics. Kinetics is about the actual physical rate that things are happening. Free energy is about the movement of energy in or out of the system. So for this lecture, your goals are to understand first order kinetics. Now, kinetics goes far beyond first order. This is a very simplified form of kinetics. It applies to quite a few enzymes, but certainly not the majority of them, and it's what's called Michaelis-Menten. There's a variant of the Michaelis-Menten called the Lineweaver-Burke that makes it a little bit easier to examine what is happening in a chemical reaction with respect to what is happening to the enzyme. So with that, we're going to be able to recognize and explain different forms of enzyme regulation. So we start here at the Michaelis-Menten equation. We know that at a given substrate concentration we will have a given velocity, so this velocity and this substrate are related. There is a theoretical maximum value of velocity the enzyme can never actually achieve, but it will approach it, and then we have the Km, which is the substrate concentration that will give us 1/2 of this maximum velocity. And you should be able to use this equation in a variety of ways, solving for Vmax, solving for Km, even solving for substrate concentration if need be. And we also looked briefly at a Michaelis-Menten style graph, and there were some landmarks: the theoretical maximum velocity, the substrate concentration that results in a velocity equal to 1/2 that maximum velocity, and the overall nature of this curve. And we see at higher levels of concentration of substrate that the curve starts to plateau as the enzyme system becomes saturated. So here's a quick quiz for you. What is Km? Go ahead and just take a moment to actually state what is the definition of Km. Km is the substrate concentration that gives you 1/2 maximum velocity of the enzyme system. If Km increases, what does this mean? If Km increases, it means more substrate is needed to achieve 1/2 maximum velocity. This gives us an idea that perhaps the enzyme is not functioning as well as previously. If Km decreases, what does this mean? This means that it requires less substrate to achieve 1/2 maximum velocity, which would typically kind of infer that the enzyme is behaving stronger than it would normally. So let's look at a drug design example. So we're going to take an enzyme of interest, just a generic enzyme. I'm just going to call it Enzyme, and we're going to prevent a dangerous disease. We'll call that death. So given the following information, does the inhibitor work? Remember, we're trying to slow down enzymatic behavior. Okay, that's an inhibitor. And if it does work, what is the new Km after the addition of the inhibitor? So what we need to know before we even go into all of this is what's happening to Km and Vmax. If we're losing velocity or we're losing activity, the inhibitor's working. Similarly, if it takes more and more substrate to actually get the enzyme to accelerate, the inhibitor is also working. This would be because the inhibitor is interfering with the binding of substrate. So we have an idea of where we want to go. We want to see either changes in velocity that get worse or increases in Km. So we start with our equation. Velocity equals Vmax times substrate concentration divided by substrate concentration plus Km. Remember, this is the substrate concentration that gives you this velocity. And in our control samples, we measure a Vmax of 100. I'm omitting units for now just so we can focus on what we're doing. At substrate concentration 20, you get a velocity of 28.57. We don't know the Km, but we can calculate that. Then in our experimental case, we add the drug. We get a Vmax of 100, and at substrate concentration, we get a velocity of 25. So before we go anywhere, we can already see the drug did work. We just don't know how well it worked or what exactly happened. And that is because our initial velocity at substrate concentration 20 was 28.57 units per second. Then, when the drug is added, that velocity slows down. So suddenly, the same amount of substrate gives us a slower response rate. This shows us that the inhibitor worked. So if it takes more substrate to achieve the same rate, so for example at substrate 20 we actually lost rate, so it would take more substrate to get back to 28.57, obviously this will have an effect on a Km, but what will that effect be? Well, we know Km is the substrate concentration that gives us 50% of Vmax as a velocity. So it would be the substrate concentration that gives us 50 units per second. But since the system is slowing down, we should expect that Km to increase because it takes more and more substrate to generate the same velocity. So we have an idea, and what we map out what we want to know. Does the inhibitor weaken the binding affinity of the enzyme for the substrate? And we're going to determine that by examining Km. What we should see is an increase in Km, which would infer that the binding of the enzyme to the substrate is weakening, or that the enzyme is not recognizing the substrate as well as it does without the drug. So to do this, we need to know the two Kms, one for control and one for experiment. So all we're going to do is simply rearrange the equation and solve it for Km. My first step is to simply get rid of this fraction. So I'm going to multiply both sides of my equation by substrate concentration plus Km. That cancels on the right side of the equation, leaving just Vmax times substrate concentration. My left side is now velocity times substrate concentration plus Km, that quantity. So now I need to isolate the Km. So I'm going to divide both sides by velocity. So now I have substrate concentration plus Km is equal to the quantity Vmax times substrate concentration divided by velocity. Then I'm going to get rid of the substrate by subtracting it from both sides. Now Km is equal to Vmax times substrate concentration divided by velocity. That quantity, we're going to subtract substrate from it. So now it's plug and chug. So Vmax 100, substrate concentration 20, velocity 28.57, and substrate concentration 20 again. Km 50. We do it again for the experimental. Vmax 100, substrate concentration 20, velocity 25, substrate concentration 20 again, Km equals 60. So we can see that the Km did in fact increase. So the Km of control was lower than the Km of the experiment. Therefore, Km increased. And that means the inhibitor did weaken the enzyme's affinity for the substrate. If this isn't clear, please go back, review the definitions of Km, review the Michaelis-Menten equation, and do this calculation on your own with some different numbers. Be sure you can work with the equation. So with all this talk about Km, does Km have any particular relevance? Well, we already know cells tend to keep substrates around their Km values to make enzyme accelerations, decelerations smoother, but is there anything else? Well, it turns out there is. So there's a disease called ethanol sensitivity, and upon ingesting even small amounts of ethanol, some people experience flushing and tachycardia. Tachycardia, if you're not sure, this refers to a dramatic increase in heartbeat, so a really increased heart rate. So it happens to be that this problem is the result of a Km mutation in an enzyme. So let's look at our reaction. So this over here is ethanol plus NAD, remember this is one of our cofactors, yields acetaldehyde plus NADH, so this went to a reduced form and releases a proton. And the enzyme that does this reaction is called alcohol dehydrogenase. And as a side note, when you see these dehydrogenases, there's almost always some sort of electron carrier like NAD, FAD, FMN, NADP, something like that. You're going to see some sort of redox reaction. Okay, so this enzyme is creating acetaldehyde. That's this material here. So the key product of this reaction is acetaldehyde, and this is the material that causes the symptoms, not the ethanol. Okay, so you might be saying, well, wait a minute, if the ethanol is not the problem and this enzyme's fine, then what's going on here? What do you mean there's a Km mutation? Is the alcohol dehydrogenase failing or something? No, the alcohol dehydrogenase works just fine. However, we have the acetaldehyde. This material must be cleared. So this material, acetaldehyde, is cleared by aldehyde dehydrogenase. And since that's a dehydrogenase, you can almost guess what that reaction is going to look like. It should involve the acetaldehyde and some form of electron carrier. So let's see what happens. There are two forms of aldehyde dehydrogenase. One is cytoplasmic and the other is mitochondrial. The cytoplasmic form is not very good. It has a very high Km, so it doesn't process the aldehyde very efficiently. The mitochondrial, on the other hand, has a very low Km and does process the aldehyde efficiently. These are pretty much isozymes of each other, very, very similar enzymes processing the same reaction. Remember, similar enzymes, different genes, same reaction, almost identical. Those are isozymes. So we have cytoplasmic aldehyde dehydrogenase, mitochondrial aldehyde dehydrogenase, and those are isozymes. Now, in people with the disease, the mitochondrial enzyme is less active owing to an amino acid mutation. One amino acid gets fouled up, and therefore the mitochondrial enzyme does not function well. This means the aldehyde does not get cleared efficiently because the cytoplasmic form cannot keep up. Okay, and it doesn't take much. That shows you the cytoplasmic form is not terribly effective at this. So only the cytoplasmic form is functioning, which means the acetaldehyde escapes to the blood and causes the effects. So a simple change in Km can result in a physiological response to an environmental stimulus. In this case, ethanol is your environmental stimulus. The Km of the enzyme does not work as well, so it's being cleared by an inferior enzyme. Compound escapes to the blood, causes flushing and tachycardia, and that is our physiological response to an environmental trigger owing to simply a Km mutation. So going back to our kinetics, we know Vmax cannot be achieved. So there should be some alternate ways to determine what is happening to an enzyme substrate system, because first of all, those curves are fairly difficult to examine, but there is a better way. So we can use what's called the line-Weaver-Burke, so also known as the double reciprocal. So in Michaelis-Menten, we plot on the x-axis substrate concentration versus velocity. Well, we could change that and do a double reciprocal. So we can plot on the x-axis 1 over substrate concentration, and on the y-axis 1 over velocity. And so this gives you this equation. 1 over velocity is equal to Km divided by Vmax, that quantity times 1 over substrate concentration plus 1 over Vmax. And if you look at that equation, you think about it, you might see something very special about it. It's y equals mx plus b. Now, y equals mx plus b, that's a line. That's not a curve. That is a straight line, where if we set x to 0, we get our y-intercept of b, and if we set y to 0, we get an x-intercept of negative b over m. So we can play with this equation using a straight line and derive very important features from it. So we're no longer examining a curve, we're looking at the behavior of a line. That means we don't have to estimate, we can calculate exactly. So here's what a line-Weaver-Burke graph looks like. Now let's note a few features. First of all, the slope of the line, m, is Km over Vmax. So if we know one, we know the other. If I know the Km and I know the slope, I know the Vmax. The y-intercept, so this is where x equals 0, is equal to 1 over Vmax. Well, the y-intercept is b in our equation, remember? If I set x to 0, y equals b. So b is 1 over your Vmax. Think about that for a moment. That's easy. Now our x-intercept down here, where y is equal to 0, is negative 1 over Km, which means I can solve for any pattern of enzyme-substrate interaction simply by looking at the behavior of the line. Now, a few things to note. This equation cannot be negative. If you have a negative b, for example, that would imply that your Vmax is some negative units per second. So that doesn't work. It must be positive. Likewise, if this term mx is negative, that would imply a negative slope. So a negative Km or a negative Vmax, either one. Of course, if Vmax is negative, you have to have negative mx and negative b. Now you might say, well, what about this negative 1 over Km? That's okay because it's negative 1 over Km. So the Km is not negative. But if this term were negative, mx, that would imply the Km is negative, which would put your x-intercept on the positive axis, and that would be incorrect, okay, because you'd also end up with a negative slope. So no part of this equation can be negative. It must be positive, even though our x-intercept will have a negative value. I know it's complicated, but play with the equation a little bit, and you can use the values we explored in the drug design example with this system, and you'll see it works just fine. So it isn't used as commonly as Michaelis-Menten, but it is important because at a glance we can tell the differences of enzymes to drugs or inhibitors. Which raises the question, should all enzymes act at full speed at all times? And the answer is no. They can't act at full speed at all times because many reactions in the metabolic systems are actually contrary to each other. Just think of glycolysis, the breaking down of glucose, and gluconeogenesis, the creation of glucose, both of which occur in the same subcellular compartment. We do not want those reactions occurring at exactly the same time at the same amount. So what we have instead is regulation. So all enzymes are precisely regulated at many levels, with the most common mechanism being some sort of feedback. Some sort of downstream product of the reaction interacts with an early enzyme in the pathway. We're going to see this all over the place. Now, enzymes that do freely reversible reactions tend to be regulated simply by concentrations of substrates. They are not necessarily going to be directly regulated the way unidirectional enzymes will be. But this is just sort of the thing I was examining, is that we have so many, here's just glycolysis and gluconeogenesis, how they all interconnect, and with various other metabolic systems, we can't have all of this going at full speed all the time. It doesn't do any good. But let's go to a little simpler system. So here we have almost our classic system. A is freely reversible to B is converted to C unidirectionally, C is freely reversible to D is freely reversible to E, and E inhibits. So this, where E inhibits this enzyme, this is a feedback system. It's also called an allosteric system, as you will see, but E inhibits enzyme number 2. And we also note that enzyme number 2 is unidirectional. So we tend to see more regulation at unidirectional enzymes than we do at freely reversible enzymes. Down here is a little bit more complicated. E inhibits its own production but promotes production of B prime. Well, activity of B prime. I promotes production of E but inhibits enzyme B prime. K promotes B, and you can see what's happening here. If you look at it very carefully, it's all designed to keep the levels of E, I, and K in balance. Let's look at an example. If E is depleted, then first of all, the brake on enzyme B will be released, which will promote creation of E. Similarly, we see if E is elevated, we slow down production of E, but we push production of I and K, because E activates B prime, which creates F, and F can make I and K. So we have different substrates, E, I, and K, interacting in ways to promote a consistent amount of E, I, and K. If K comes out of balance, it slows down its own production, promotes production of E, and E will promote production of F, which will promote production of I. But remember, F is not going to promote production of K because K was out of balance and slowing itself down. So in this way, E goes up, I goes up, and they're all back in balance. These networks do get complicated, so spend some time thinking about it. Our most common form of major regulation is feedback inhibition. This is control of a product is determined by the products themselves. So if we go back, E blocks its own formation. Very, very common, because usually this is some sort of energy intensive or material intensive system, so we don't want to waste it making product that is not necessary. And this will be accomplished by allosteric regulation. So an allosteric enzyme, which are usually unidirectional enzymes found at particular rate limiting or committed steps, have an additional binding site called a regulatory site. Now, the regulatory site is not the active site. It is not where catalysis takes place. It is an additional pocket on the enzyme where material can bind, regulatory material. Materials that bind here can activate or inactivate the enzyme. It is entirely material and enzyme specific. There is no general rule. And they do not take part in the catalysis. They don't take part in the reaction in any way. They simply either allow the reaction to proceed or inhibit the reaction. It does not also, by the way, interfere with binding. The substrate still binds at the active site, no problem. Just the regulatory site will control whether or not catalysis is occurring. So here, this is a fairly complex pathway. We see we have many reactive feedback style inhibitors, or molecules, and so we see these two pathways coordinate to make K. Okay, so what happens? So let's assume we need some sort of ratio of F to I, but there's more F than there should be. What happens? Well, first of all, F inhibits its own production, feedback. So the amount of F being made lowers. I will then catch up because the amount of F being made is slowed down, and since we have an overabundance of F, if we follow this dotted line here, we see it activates enzyme number 10, which will promote the formation of I. So if F is in overabundance, the creation of F slows down, and the formation of I speeds up in an attempt to restore the balance of F to I. Those will go on to form K. If K becomes overabundant, it slows down the formation of F and slows down the formation of I. Don't worry that the lines are dotted or solid. They're just doing that to make it clear, so it's not all just solid lines everywhere. So we have sensors. F senses its own abundance. If it's, because enzyme 1 senses the amount of F. If F is too high, it slows down. Enzyme 10 senses the amount of F. If F is too high, it speeds up to make, I'm sorry, if F is too high, enzyme 10 speeds up to make substrate I. If I is in overabundance, enzyme 10 senses that and slows down. Enzyme 1 senses that and speeds up to create more F. If K becomes overabundant, enzymes 1 and 10 can both see that and will slow down the formation of the whole system. So, as we see here, I stimulates its own production. I inhibits its own production by blockading E10 and stimulates production of F, activation of E1. F inhibits its own production at E1 and stimulates production of I at E10. All three products, F, I, and K, coordinate to keep the system stable. So now that we know enzymes can be inhibited and we've seen a little bit about feedback inhibition, it bears mentioning that there are many types of enzyme regulation, not just feedback. And these are competitive, where we have inhibition at a binding site, non-competitive, where we have inhibition at some allosteric or distal site, uncompetitive, where we have inhibition at the binding site, but that requires the substrate to be present. This one's really weird. Suicide inhibition, where there must be chemical reaction, but then the enzyme is ruined afterwards, and transition state, which is very difficult to explain, except we're going to create an inhibitor that mimics the transition state, and enzymes are just shut down at ridiculously low concentrations of inhibitor. These are crazy. So, looking at competitive inhibitors, if we have an enzyme, and it has a pocket to bind a substrate, and notice it has a side pocket here, a competitive inhibitor simply blocks the pocket. It just binds with the enzyme. It does not undergo catalytic reaction, so therefore no product can be made. But it does prevent the enzyme from recognizing the substrate, because some amount of the time the enzyme is binding to the inhibitor and not the substrate. So think about it. What does that do to Km? Or Vmax? Or both? Well, going forward a little bit, the inhibitor binds reversibly, so it can be spit out. There are intermolecular bonds, are standard, hydrogen, electrostatics, all that. No reaction. And the inhibitor depends on the strength of inhibitor binding and inhibitor concentration. Substrate cannot bind. Increasing substrate concentration will reverse this inhibition because the substrate will outcompete. And the inhibitor should be similar in structure to the substrate, which means what we should expect is an increase in Km. So it should take more substrate to overcome inhibition, return to 1/2 Vmax in terms of velocity, which means this entire curve shifts right. But if we look at a Lineweaver-Burke system, what will happen is Km will increase, which means our slope increases, but the x-intercept will decrease because Km's getting, remember, we have a negative denominator. All right, so we go from, say, let's say we go from Km2 to Km4. We would go from, call it 2 over 1 to 4 over 1. So that's a dramatic increase in the slope. And then we went from negative 1 over 2 to negative 1 over 4, which means our x-intercept is moving closer to 0. So we should basically see this entire line kind of rotate around the y-intercept. So this just gives you an example where we have our competitive inhibitor, and you can see here that our Km is steadily shifting outwards. Now, uncompetitives, since we're working with the active site, let's look at uncompetitives real quick. Uncompetitives are very strange. An uncompetitive inhibitor binds with the substrate and the enzyme. So it requires all three parts, the substrate, the enzyme, and the inhibitor. And what it does is it actually increases the odds that the substrate will find the enzyme, or that the enzyme will find the substrate. So it's making the ability of the enzyme to bind to the substrate better. So what does that do to Km? We should expect that that will lower the Km because the enzyme is finding the substrate better, as better affinity. It takes less substrate to get to 1/2 Vmax. So you might say, well, why is this an inhibitor? Because the uncompetitive inhibitor actually blocks catalysis. So since catalysis is being blocked, we can't actually have product formation. So what will that do to Vmax? That should lower Vmax because our overall catalytic rate is lowering. So now we know what should happen. Km should decrease, Vmax should decrease as well. So both drop, Km drops and Vmax drops, which gives you these weird curves where the Km is going further and further down, but remember, it's still relative to Vmax, or Vmax values are going down. So Km drops and Vmax drops, and easier to see with a Lineweaver-Burke, because if we think about it, we're going to have a change in the slope, and since we're dropping the Km, the x-intercept will move further away from 0. So you end up with a very different looking graph, something more akin to parallel lines, as you will see. Now this is the non-competitive inhibitor, the allosteric inhibitor. This is very, very common for feedback inhibition. You notice the inhibitor binds at an active site, at an allosteric site that is not the active site, but does not prevent substrate binding at all. It doesn't improve it, doesn't block it, doesn't do anything with binding. So what happens to Km? The answer would be nothing. Because there's no change in binding, Km will not change. So what we do have is a loss of catalysis. So what does that do to Vmax? Well, Vmax should drop. Remember, we lose catalysis, Vmax drops, but we're not changing binding, so Km will stay the same. Now, do not let this confuse you. The value of the velocity that the Km gives you will decrease, but remember, Km is a concentration, not a velocity. So we can see here the Vmax is dropping, but actually the Km to give you that 1/2 is staying the same. It's right about here. So, real quick, let's look at our Lineweaver-Burke graphs and see if we can make sense of what is going on. So let's look at this graph. What do we have here? Well, we have an increase of slope, and we have a change in the x-intercept, but no change at the y-intercept. This means Vmax did not change. So Km changed. Km got higher because remember it's 1 over Km, and we're moving towards 0, so we may have gone from negative 1 over 2 to negative 1 over 4. So 1/2 to 1/4, closer to 0. And our slope increased, which means Km increased. Vmax did not change because our y-intercept. So if you said competitive inhibition, you are correct. Now let's look at this one. This one we see two parameters have changed. Our Vmax has gone from, say, we're changing our Km, we're changing our Vmax, our slope has changed. Well, our slope hasn't changed because both parameters changed. Our Km went from, say, negative 1 over 4 to negative 1 over 2, so our Km dropped, and perhaps Vmax did the same thing, negative 1 over 4 here, 1 over 4 here, 1 over 2 here. So Km dropped, Vmax dropped, both things dropped. If you said uncompetitive inhibition, you are correct. And now let's look at this one. Here, again, only one parameter's changed. Km did not change. So that means binding was not affected by the inhibitor. So our Vmax maybe went from 1 over 4 to 1 over 2, and then suddenly we see our Vmax dropped, but binding did not change. If you said non-competitive or allosteric, you are correct. Now, let's talk briefly about transition state inhibitors. Transition state inhibitors are very difficult to come across. They're very rare, and what it is essentially an irreversible binding to the catalytic site. There's no way to get it out of the enzyme once it's there. And that means the cell will have to simply eliminate the enzyme. However, by eliminating the enzyme, the cell releases the transition state inhibitor, which immediately binds to another enzyme. Well, the same enzyme, another member of that population. So transition state inhibitors are almost absolute elimination of enzyme catalysis. And they do this without making a single covalent bond. Remember, the transition state of the enzyme is energetically stable because it's a very low energy point. So what we're making is an inhibitor that in its stable ground state mimics the geometry of the substrate in its transition state. So let's take a look. You don't have to worry about all this. Let's just look down here in this little box. We notice the reaction intermediate has these two hydroxyl groups on this carbon, and so this is our stressed state. So the inhibitor has one hydroxyl group. It is unstressed, and it's just close enough to this geometry that the enzyme recognizes it as substrate and moves to the enzyme moves to its own transition state and locks down, and that's it. The enzyme is toast. These inhibitors work at concentrations of 10 to the minus 15, which is femtomolar, whereas most drugs you're looking at picomolar to nanomolar. So minus 12 to minus 9, which means a transition state inhibitor is about 1,000 times more potent than that. They're ridiculously potent. Suicide inhibitors are also irreversible inhibitors. However, these are substrate mimics. So they look like the substrate, except they have a chemically reactive point where catalysis occurs. So instead of simply producing product and being released, it actually forms a covalent bond to the enzyme. So you might hear these as competitive irreversible inhibitors because they're competitive because they bind to the active site like the substrate does, but they're irreversible because catalysis takes place and the enzyme is removed. Often time dependent, their structure is going to be similar except for the reactive mode. One last note. The addition or removal of phosphoryl groups from a protein is extremely common to modulate protein activity. Now, there is no rule that says addition of a phosphate results in activation or removal of a phosphate results in inactivation or anything like that. It is entirely enzyme specific, so a given enzyme will respond uniquely. There's no common rule. Now, kinases, as we will see a lot of these, kinases add phosphates to serine, threonine, or tyrosine, or all of the above residues on their target enzyme. So kinases add phosphates to serine, threonine, or tyrosine. Phosphatases remove phosphates from their target. And remember, our big key are serine, threonine, and tyrosine. So with that, that's it. What I'd like you to do is be sure to go back, look at the modes of inhibition, look at their signatures in terms of graphing, be able to work with the Lineweaver-Burke graph and the Michaelis-Menten graph, work with the equation, understand how feedback inhibition or feedback activation helps coordinate multiple metabolic systems, and be sure to really intuitively understand what's going on physically as well as mathematically in regards to inhibition. And with that, we'll be ready to move on to our third and final chapter of the enzyme epic.